equations are essentially the same, correct? Second order, this is the negative coefficient, yeah, essentially the same, second order ODE. So then we don't solve it, we just look at the solution for the phi. This. So what is the coefficient? Square root of the coefficient. Yeah, we just put this one, right? With the c squared. Yeah, that's the only difference. So here the H general solution, from here we get general solution, the function of t should be in this form.
Alpha cosine square root of pi, lambda, well, c squared will be between, so it'll just be c, right?
Yeah, c squared can be taken out.
Taken out and just c.
Yes, just c.
Times t plus.
Times t, yeah, instead of x. So here is so if you just recognize this is the same structure, right? We can put the whole thing in the place of lambda. So exactly the same kind of representation. Yeah, so we have h now, the function h. So you have a function phi and h, then certainly for each lambda we get an h, right? So we put a subscript. So for subscript, because for each lambda you get a phi sub n. For each lambda n you get a h sub n. So then you multiply for each lambda you will get a pair, right? A phi n and hn. Okay, so we multiply them. So right now we will, for each lambda n, we can get a product, which will be a solution of the PDE problem. So at least we know this product will satisfy the equation, right? Will satisfy this, but not yet the initial condition. Yeah, so we used all the conditions. So here we have this form. Each one is a solution, but we have a superposition principle for homogeneous equations. That is, if you have this as a solution of that problem, any arbitrary combination of the solution will still be a solution. So we can actually apply superposition principle. That is, any linear combination of the solutions will satisfy homogeneous equation as well, and also homogeneous boundary conditions. So n from 1 to infinity. So we can do so let's call it U, this U. In the series form, right? A more generalized form is in the series form, which is this form. And that's the arbitrary coefficient in front of this. And from 1 to infinity. Yeah, so here we have a solution. And we can take the h and phi and substitute them into the representation. So let's get a more specific form. So here, what is the phi? Is this, right? Just the sine function. H will be this function with two terms, cosine sine. So with some coefficients. So the arbitrary coefficients times that so we can also put this because for specific n, the coefficients also can be differentiated. Okay, so here, so the alpha n, beta n multiplied by Cn still a coefficient, right? Some constant. So eventually all this can be written as this is phi. Phi I put phi n times instead of using alpha, so I use a sub n cosine. Cosine, what's the square root of lambda, which is this? Right, square root of lambda. And square root of c squared is a c, so I put a c here. T. Sine. C. T. Okay, double check. Okay, I use this because basically it's just Cn times alpha n, right? Cn times alpha n is still another coefficient. We can call it a sub n, it's just one coefficient. So Cn times beta n, that's also a coefficient. Let's call it capital Bn. So basically it's this form, and then so the U in infinite series form, right? The solution in the infinite series form is this. So finally, after we look at this boundary condition, this PDE problem using separation of variables, we arrived at a solution in this representation. Okay, so next A and B and are coefficients, right, to be determined. So remember, we haven't used all conditions, so then the initial condition will be used. So here, the first initial condition, second initial condition. Then we have two sets of coefficients to determine. Okay, so here, let's work together on the one set of coefficients, the other set of coefficients in the series. Just direct the substitution. Yeah, next let's substitute t equals 0 into the solution. Yeah, so make t 0, then make it equal to f. F is the given function. Okay, so next we use the initial conditions. So let's look at the two initial conditions. First, when t is 0, so that u, when t is 0, yeah, what is gone? This one, sine term is gone. Yeah, all the b terms, right? All the terms involving the b coefficients are gone. So this one will become 1. And that's an times this. It's a function of x. That's very good, a function of x in series form compared with the f, right? Okay, that's a function of x, which is also the u. Yeah, we just put an sine function of x. Okay. Well, notice that actually this assume f can be expanded into Fourier series form. Those are orthogonal functions, right? Orthogonal functions. If f can be expanded in the Fourier series, then also suppose the series converges. Then we can determine the coefficients, series coefficients, right? How do we determine? Those are orthogonal functions. Yeah, orthogonal functions. In order to determine each coefficient, suppose I want to determine the m, the because m can be the first one, right? A1, for example. Yeah, if I want to determine when m is 2, that will be A2, right? So how can I determine in general the mth coefficient? So we try to use, make use of the orthogonality of the sequence, that sequence. AM, okay, associated with what? Sine m pi over L x, right? It is associated with that. So for so many terms, let's use, so f, left side and right hand side in this equation. Left side, you multiply by this function, when this is m. Okay, so right hand side also term by term, right? Each term will be multiplied by this. Keep in mind we want to look for the coefficient of m. So we just use the m sine function, sine m pi over L. Multiply both sides of the equation. So term by term, both sides. So here, this is still equal, the equation. And then we do integration, integral from, for the length from 0 to L, dx, to integration. Because this series assumes it's convergent, so we can differentiate integral term by term, right? Integral from 0 to L, and from 1 to infinity, dx. So after you multiply and integrate from 0 to L. Now, they are orthogonal functions, right? They are orthogonal in this, that can be viewed as a inner product. So whenever n is not equal to m, it will be 0. Actually, remember this is orthogonal function. If you multiply n and m dx to integral, that will be 0 whenever n is not equal to m. So orthogonal. When n equals m, what do we get? Half of m. So when m happens to be the same as n, then when they're equal, then it's not 0. So all terms will be 0. You see, only m's term is a non-zero, right? Only m's term. So all this infinite series will drop to one term, which is the mth term, which is am, with the am coefficient, and the integral of that is half of f, right? Yeah, so that's the right hand side. The left side is this integral. Then we found the coefficient, the mth coefficient. M can be 1, m can be 2, right? M can be anything. So then you found the mth coefficient, which is that divide this. So which is yeah, so here are how many? M from 1 to infinity. So all the coefficients can be found.